In this video, we're going to take a look at rational functions using transformation. So a rational function is a function that can be written in the form f of x equal to p of x divided by q of x, where p of x and q of x, they're polynomial expressions, and q of x cannot equal 0 since we can't divide by 0. Now, similar to the radical functions which had restrictions, rational functions will have something called non permissible values. Now, these non permissible values are based only on the denominator of the function. So it doesn't matter what's happening in the numerator, we need to only look at the denominator for the non permissible values. So if you take a look at these three examples, the first one has a denominator of x, so we say that x cannot equal 0. The second one has a denominator of x minus 3, and again the denominator cannot equal 0. So therefore x cannot equal 3. And then the last one, 2x minus 3, the denominator cannot equal 0. So 2x cannot equal 3, and then x cannot equal 3 divided by 2. Now you'll sometimes see in textbooks where it actually says x equals 0, x equals 3, and x equals 3 over 2. It's just how the textbook would like to say it or state on non-permissible values. So for example, here it says state the non-permissible values. If we read it out, we could say the non-permissible value is 0, is 3, and it is 3 over 2, as opposed to it is not. Now, we're going to graph rational functions using a table of values first, so we can look at some features, and then we'll go on to transformations. Now, when you're graphing using a table of values, it's probably convenient for us to identify the non-permissible value, so you can use that non-permissible value as a middle value in your table of values for x and y. So we're going to take a look at these two examples. We're going to analyze the functions, and then we're going to look at some of the behaviors of the function. So this first one here, like I stated, we should start with a non-permissible value. And in this case, it's going to be x equals 0. Or you can say x cannot equal 0. Now, for the rest of the features, we're going to use the graph to analyze it, and then we'll come back to fill it in. So here we have x and y, and we're going to place our non-permissible value of 0 into the middle of our table. And we know that's going to be undefined. And then we'll choose a couple of values on either side. So I'm going to go -2, -1, and then 1 and 2. So when I plug in -2 into my equation here, I get 1 over -2, so I get -0.5. Plug in -1, I get -1. 1, I get 1. And I plug in 2, and I get 0.5. Now, to start by graphing, I recommend that you start with that undefined value. So when x is 0, we get undefined, and that is represented by this dotted line, which actually is called the vertical asymptote. Now, for the purposes of right now in this example, we also have a horizontal asymptote. And you'll see this when I do some graphing. So I'm going to plot the other 4 points. So -2, -0.5, -1, -1, 1, 1, and 2.5. Now, if I choose another point, let's say to get a better understanding of what happens, if x is half, I have 1 divided by half, which means that I also have a value of 2. So at half, it is 2. Now, the nice thing about rational functions is that they're actually symmetrical. So since I have positive half and 2, I'm now going to have -0.5 and -2. So I can connect my 3 points on this side. And then I'm going to connect my 3 points on the left side. And that is what the rational function 1 over x looks like. So let's go back to looking at the features. So the second piece says, what is the behavior near the non-permissible value? Our non-permissible value 0 is asking what's happening near 0. So when I look at the right side of the graph, near 0, the y value is getting very large. If I look at the left side of 0, the y value is getting very, very small. Now, I could say large and small, but what I can also say is it's becoming a very large positive number on the right side, and it's becoming a very large negative number on the left side. So what I'm going to say is, as x approaches 0, y, no matter whether I approach from the right or from the left, the y value is becoming very large, whether it's negative or positive. So I'm going to put absolute values around the y, because if it's negative or positive, it still can be taken into account. So the absolute value y becomes very large. The end behavior is asking what happens to the y values as x approaches the end of the graph. So as x gets larger and larger, we can see that the graph is getting closer and closer to a y value of 0. On the left side, as x gets larger and larger negatively, the y value is still getting closer and closer to 0 as it approaches this red dotted line, or we can say the x-axis. So what we can say is the end behavior is, as the absolute value of x becomes very large, meaning whether I approach positive infinity or negative infinity, the y value is going to get very close to 0, or y approaches 0. The domain, when we're looking at the domain, we can see that it's all the numbers as it goes on and on, left and right, but at the asymptote it doesn't hit the y-axis. So we can say that x such that x cannot equal 0, but x is a real number. And then we can put curly brackets around that part. In terms of the y, we can see that the y goes all the way down and all the way up. But again, it doesn't hit this horizontal asymptote this time. So we can say that y is such that y cannot equal 0, but y is a real number. Now, similarly to the domain and range, the equation of the vertical asymptote is saying, what is the equation of this red dotted line? So this red line is hitting an x value of 0, so we say that x equals 0. So it's actually, you'll see that it matches our domain, but instead of cannot equal 0, x equals 0, since it's an equation. The equation of the horizontal line, asymptote, is a line that hits y equals 0. So we say that y equals 0. All right, let's take a look at the second one and compare it to the first one. So if you look at the numbers, we can see that the only difference is that there's a 3 on the top. So let's see what happens with that. The non-permissible value is still x cannot equal 0, since that's what's dividing on the bottom. So we're going to place that in the middle of our table. Pick 2 numbers on either side. And this time we get negative 3 over 2, negative 3, 3, and 3 over 2 when we plug it into this equation. So again, we're going to start with my asymptote on the y-axis and the x-axis. Plotting my 4 points, I get negative 2, negative 1.5, negative 1 and negative 3, 1, 3, and 2 and 1.5. So I'm going to connect these 2 points on this side, and I'm going to connect these 2 points on the left side. Now you can see if we compare the 2 graphs that the right graph looks just like the left one, except that it's expanded by, it seems a little bit further away from the origin. When we take a look at the y values, we can see all of the y values are multiplied by 3. So actually the graphs are almost the same, except it's 3 times larger in terms of the y value. So in terms of what's happening with these features here, everything actually is identical. So as x approaches 0, the absolute value of y, it becomes very large. And we can see that it's approaching very large y values and very large negative y values. The end behavior, as the absolute value of x becomes very large. So whether it's approaching positive infinity or negative infinity, the y value again is approaching 0. And then finally, the domain is x cannot equal 0, range is y cannot equal 0, the vertical asymptote is x equals 0, and the horizontal asymptote is y equals 0.